Yeah, thanks a lot, CP India, for taking up my paper at first and giving me the opportunity to speak to Indian community, especially who are into CPP. So let's quickly start. So I'll be sharing my screen. Yeah. So I think you can see the screens, right? One is the VS Code, which is running with examples, and then one is with the PPT itself, right?
Yes.
Okay. So yeah, I think we are good to go. Yes, I'm starting now. Yeah. So yeah. So this is the session where we'll try to understand the concurrency patterns with some tricky examples in both in real time and as well as non-real time examples I have here. So moving on to myself a little bit. So I currently work at VITES GmbH, Munich, Germany, mainly focused on design and development of software for satellite communication systems, for ground station terminals in general, which is primarily dealing with C and C++17 for an embedded Linux platform on Zinc processor. So these are my contact details. Yeah. So all the PPT and the code will be available on my GitHub. I will try to give that GitHub link through CPP India, and then moving on to today's agenda. So I'm not going to deal much with the definitions part. I am trying to give more insight into examples and then try to qualify the examples with Valgrind as a tool, as a mem check, memory checker, and as well as a thread checker, thread error detection. So today we are going to see about a little bit about concurrency, how it is from the definition part, and then we see some classic problems and their solutions, solving them using C++17 and 20 with different kind of combinations. We have asynchronous way of doing it, and then also with the synchronous and then normal thread, how it works. And then I have a special thing here that is asynchronous IO with a reactor pattern using libuv as an case study here, where I try to showcase you three set of examples where how to actually understand the event loop in depth, and then try to come out of it shutting down the event loop. So this is the basic example which I took, and then we try to play around with Valgrind a little bit. So and then the final thoughts on concurrency itself, and then we have some good references where you can try to explore yourself about concurrency. So all in all, this session is about you get a set of examples where you can try to scale them to your requirement, and also try to see how you can design a data structure for concurrency. So this is the core topic today. So let's see about a little bit about basics on concurrency. So concurrency is a technique which is used by many processes these days to allow multiple process to use the cores and then manage the shared resources using context switching actually. So if you see on the right side, you have three threads actually: thread A, thread B, and thread C. And then core 1 and core 2, they're trying to play around with each of the thread uh, with certain algorithm, actually a certain scheduling algorithm in general. So how it is achieving it's two threads. They are the lightweight process which are allowing the CPU to quickly play around with this, switch them in real time. So let's see what are the basics of concurrency. That is, we also saw that this is the concurrency, and then what are the advantages we are going to get when we use concurrency in general. So we'll have a throughput, improved throughput and efficiency, better CPU utilization, and then you will allow concurrent access for multiple users. And then this is also used for real-time applications. And yeah, so this is it. And of course, it poses a lot of challenges. How to design that and how to tailor make those data structures, it's quite critical. And then what are the challenges in general? They have race conditions, they have deadlocks, and they have starvation, and then they have live blocks. So, okay, let's briefly see how to overcome these challenges. We have something called concurrency patterns in general. So if you see on the left side, you have concurrency architecture where you can model your object according to these active object, monitor object, and reactor. I will try to go through them in the examples itself. So, and then we have some synchronization patterns, how to deal with the sharing of the data, and also future variables, and also we have how to deal with the mutation itself, to deal with the mutexes, and how to do some strategized locking in general. So this is the brief overview of the concurrency patterns. So let's move to the good example of it. As classic example, first number one is the sleeping barber, where I have a barber, and then let's assume that we have a barber, and then we have a waiting room, and then there is a customer here. Um he is trying to come to barber for a haircut, and then in case if the barber is busy, he'll try to wait in the room, or in case if the waiting room is full, he'll try to exit the barber shop. So in this example, what I assumed is the waiting room is our monitor object. So it will try to notify both the barber and the customer about the status of the barber and also the customer. So this is how I assumed, and then I'll see the implementation. So the tricky part here is, let's say if there are no customers, then the barber can sleep, and the barber customer has to wake up and then have a haircut with him. And then in case if the barber is busy with the customer can wait in the waiting room if it's not full. So this is the overall scenario. So what are the objectives which I put in my model is to do not have any race condition, to don't have any starvation in general, and to know deadlock, and then there should be mutual exclusion, of course, and then efficient resource allocation in general. So let's quickly see how this can be implemented through the code. Okay, so I hope everyone can see the screens here, see the code. Okay, let me quickly give a little bit about what kind of processor I'm using. So I'm trying to just go through my uh, technical details of my laptop. So it is actually 12th gen Intel Core with i7 processor, and then this is important, and then also 64-bit, and then let's see the RAM in general. So this is using a 15 gigs RAM. Of course, 15 gigs is on Windows, and other 15 gigs is for Ubuntu actually. So right now, whatever you're seeing is a virtual box. It's a virtual machine running with Ubuntu 23.04. So yeah, so let's go to the examples now. So first, I'll try to see what the main function is trying to do here. So here we have, I took some maximum customers as 100, and then maximum available chairs as 10 actually. And then I have a barber shop object, and then the barber himself, and then the customers. So we'll try to each customer is a thread here, and then each the barber himself is a thread, of course, and the barber shop is a monitoring object here actually. So let's try to see the barber himself. So here the the code is quite simple. We'll try to see if the barber shop is open, and then yes, and then the customer will get notified, and then we'll try to run some loop actually. So first he'll try to sleep, and then check, and then do haircut, and then finished. And then in case if the I took in case if it wants to close, it will break the loop and it gets closed.
Ravi,
So yeah,
one request. Can you just increase the font size a little bit?
sure. Yeah, is it okay?
Bit one more font. If possible.
Is it okay?
Yeah, it's good.
Okay. Okay. So this is what it is. And then, okay, so let's see the barber shop itself. Basically, what it tries to do. That is the quite interesting part to see. What it tries to do is first try to set the shop open. We have a condition variable. Let me go through the barber shop class itself. So we have all the notifications and all the setting the customers and everything here. So we have some condition variables for the barber and the customer. And then I have a queue here. So I took a queue here to to make the fairness, actually, to maintain the correctness and the fairness, so that it will be served in a first come first serve basis, and also to simulate once the queue is full, I will try to quit, actually. So once the queue is full and it's got emptied, I'll try to quit. So for the simulation purpose, this queue is helping. So, and then we have some I'll try to play around with these things whenever there is a notification from the barber or the customer in general. And the customer himself, actually, he'll try to customer code is very simple. He'll try to see is the shop open, and then he will say that he is available, and then he will try to see the barber notification, and then he'll try for an haircut. The try haircut is something like it will try to see if he can get into the waiting room or not. So that is the key point here. And then once he gets in, he will notify. In case if it's not the case, then he will try to leave the shop. So here I prepared some outputs. So let's see them. So, okay, let's see how far the main problem in concurrency every time is graceful shutdown is one of the problems. And then when you give a lot of stress test, the point is you will not be able to quit the application. You will always end up in hanging the application. So let's see how this code will try to behave. Okay, the check one is okay. So if you see, it has no errors in general. One second, let me take this out. Yeah. So if you see, there is no problem. It is not hanging at any point of time. So, but for now, this is not the only qualification check where you have to be sure. You should check for memory leaks. So how we are going to do that? So there are two things which I'm going to qualify my design through Valgrind, both on memory leaks as well as thread error detection. So let's see how this will behave on Valgrind with for mem checks. Yeah, all right. So you have zero errors and no issues with mem checks as well. And then let's try to qualify the most critical part is the thread racing conditions. Yeah, so you are pretty much qualified on a very basic level how this design has to be qualified using the Valgrind I showcased you as an example, and then check for memory leaks as well as the tool thread error detection. Okay, so this is the first example. So let's go back to the second example to dining philosophers. This is a quite an interesting problem again, where you have five philosophers, okay, and then you have five chopsticks, and then they have to serve spaghetti or something like that. But the condition here is, let's suppose uh, a philosopher wants to eat something, then he has to see both his left side and the right side partner are not eating, so that he can grab the chopsticks and then he tries to eat. So here the main concern is you will have starvation, and you will have mostly you don't have fairness, and then you'll also have problems in how you will occupy these philosophers in a given time range. So that is the main problem here. So in general, these are my objectives which I choose. Like there should be no race condition, no starvation, no deadlock, and mutual exclusion should be there. And then there should be an efficient resource allocation. So let's quickly go to the examples. So yeah, this is my second example. Let's see how this is going to be possible to achieve. So I created a simple async out. This is quite common for all the classes, all the projects which I designed. This is simply for some studying out some value with a mutex lock. So let's see chopstick. So I modeled using this as a share state model. Actually, what I try to do is I tried whatever the objects to follow a solid principle and try to make them precise so that you can try to play around with it a lot, and then you have a lot of access to make them easy make them easy to scale it. So this is a chopstick class where you have an ID for it, and then you have a free option, and then it's picked up or lay down. So this is going to show your status whether the chopstick is busy or not. And then you have a dining surface, which is a very simple class, which is a simple interface for the philosopher. How he will try to wait for the sticks and lay down the sticks and wait for if it's a conditional delay. So and then I prepared a simple display class, how we are going to display the outputs. And then moving to the main class itself, main function. The table is the key here. Table is the one which is going to monitor the status of each philosopher, and also assign the chopsticks, and also do verify the queue actually. So yeah, once we start the program, it will start it, and I gave a counter for 7 seconds to play around the simulation, and then max philosopher wait is around 3 seconds. So and the max philosophers is 5. So it will try to wait for 7 seconds and then terminate by itself. So this is the pattern which I choose for this project. So let's go to the philosopher. Philosopher working is quite simple. He has 3 tasks to do. One is to think for certain time, and then he has to wait for his turn to grab the sticks, and then try to eat, and then lay down the sticks. So these are the simple steps which he has to fulfill it. But he also should maintain the occupancy, starvation, all these concurrency problems has to be maintained in this. And then, of course, there should be also fairness in this. So let's go to the most critical part of the code. So, okay. So what it tries to do when we create the table, it tries to create the philosophers, and then the sticks, and then the allocation of the sticks, how it has to be managed. And then yeah, so here he will think for certain time. Think is nothing but he will try to think for some random time, and then he'll wait for the sticks. So what am I doing here? Actually, I'm trying to lock it, and then I have a DQ here, which is more or less working like a priority queue in my project. And then he will try to push back his ID, and then he will see whether can he eat or not. So in case if he cannot eat, he will try to wait in this loop, and then if it's successful, then it will be erased, and he will try to notify, and then he will pick up the sticks, and then he will eat, and then just lay down the sticks. So this is what is the normal operation. But the most critical part is the can eat functionality. So the can eat functionality is something pretty simply designed. It's I gave the comments here to ensure the correctness. What I did is I should check whether first the adjacent left and right are free. That is the first condition. And then also in case if he is waiting, so I have to see if the MID is matching to the front of the queue so that he'll get the opportunity to eat. So if that's not the case, then we will try to see if there are if let's say 1, 2, and 3, and 2 is the middle, and 1 is the left, and 3 is the right. So we have to see if 1 and 3 are also adjacent, are also waiting, then 2 can grab it actually. So this is what is happening here to calculate the adjacent in the list, in the queue in general, and then try to grab the chopsticks and then try to have it. So this is a key part here. So other than that, I think most of the design is quite simple and mostly followed through solid principles. So let's quickly see how this is going to work. And mainly our qualification is it should be qualified both with Valgrind memcheck as well as the Helgrind. So let's see if it's really working. So you can see here the CP simulation, and then T for thinking, E for eating, and then W for waiting or want to eat. So if you see here, it's when it's across, so he is terminated. So it's all okay. So in this model seems like working. It has no hangups in the first run. So let's try to go through the Valgrind, what Valgrind says for us. Yeah. So this is the situation. We don't have any mem leaks at the moment, and you have 0 errors. Let's try to qualify this through Valgrind again for the thread error detection. Yeah. So these are the numbers are the iterations, and then we are 0. We have 0 errors, and so this is a we can model the dining philosopher model with a more precise control on occupation and starvation and fairness and correctness. So this is one way of achieving it. And then of course you should also take care how do you qualify this in the using the Valgrind. So that is a check for here today. So yeah, so moving on to the third example is the readers writers problem. So in general, readers writers problem is quite everyone knows it, but I just want to simulate it once again to see how it behaves with the modern C++. So let's, what is the reader writers problem? So basically, I created a simple database where readers can access the database without any problem. They can do it. And at that point of time, writers cannot enter, and then when a writer is trying to write something, no reader can enter. So all in all, what we know is we need a reader writer lock, which is nothing but a shared mutex lock in the C++, which is already available. So but the key takeaways here actually is, what is the objective? Mutual exclusion for the writers, yes, and there should be no writer starvation. So no writer cannot keep on writing it, and then no reader writer starvation, that is also important. And then multiple readers should be allowed to access the database. And then last but not the least, read copy update consistency. So mostly this case is handled only in kernel for most of the cases, because it's quite tricky and complex in readers writer problem. So I can briefly tell about what is the read copy update. So basically what we have to do in the design is, always you should have a snapshot of the database, so that reader can read it, and then also writer can write something with the, I mean, let's say you have a database and you have a database snapshot. So snapshot should be available for all the readers, and the database should be available for the writer so that he can make the changes, but at the same time it's not affect the snapshot. So that is one tricky part. And the new readers has to access the database, not the I mean, the snapshot database has to be updated when there is an update on the database. So that is through notifications you can do that. So this is in general read copy update. So let's try to see how we are going to simulate this using the um, C++ 17. So reader, writer. Okay. So then, okay. So let's quickly go through the example. So here, what did I do is quite a simple thing. I just created, I just made database class, and then I have a reader. I have a reading option, and then which is like shared log, of course, and I use a unique log for the exclusive access for the writer actually. So what I'm trying to do is I'm trying to I use a vector here, try to write some things, some values in 64 into the database, and then try to read it back. So in general, what I did is I took for this thing I used an async way of achieving it, and of course there's a shared reference for the database. So and then what I did is once the things are done, I will try to have a shutdown flag and then gracefully shut down the application. So let's quickly see how this is gonna behave without the Valgrind. So yeah. So what is the assumption which I made here is I have around 100 elements, and then there are five writers, and then there are 30 readers actually. I just want to simply tell about the CMake list. So CMake list has two targets. One is RW and RWV, which is actually prepared for Valgrind. And then here I have a sanitizer for thread, as well as it's uh, fully protected for stack. It has a stack protection strong actually. So this is a for every project. This is the same. So I think we are qualified with the initial hung up problems. And then we'll try to see how we can how it behaves with the mem checks. Yeah, so we don't have any errors in general. So this is quite okay. Then let's try to see if there is any race condition. Yeah, so we don't have any race condition at the moment, and then I think it's quite okay to uh, use this in general. But of course, it all depends on the application and the futures. So yeah, so this is I just want to say there is no worry about the code. Definitely, this code will be public both in my GitHub as well as the CppCon GitHub. And then last not but the least, we have a special case study on the asynchronous IO. So this is something which happened in real time for me when I was trying to achieve a TCP IP communication with an synchronous IO. Uh, but my team decided to not to go with the synchronous IO and not to do with that fashion. We wanted to explore asynchronous IO so that we can scale it up easily for any number of connections for the real time application. So yeah, let's get to the other part of the world, that is synchronous and then asynchronous. So let's see what exactly is asynchronous is actually. So so the point here is, yeah. So let's suppose you have some clients here, and then they are making some requests, and then what asynchronous IO is all about is it creates an event loop which is non-blocking. It's a single thread non-blocking, and then you have, if it's like, let's say it's a blocking IO, then it tries to create some workers and then get the response back with a callback. So then you get the response back to the clients. So this is what it is in general try to do with the asynchronous IO. So what is the advantage of it? So the mainly the time consuming tasks can be run in background, and then you can proceed with the further tasks. So that is the biggest advantage you get in the asynchronous IO. And then you will not block your CPU only for one particular task. You will try to scale it up. Any number of clients can be connected, and then try to respond based on the execution handler, how it behaves. So let's see furthermore. As a case study, I took a libuv as an example. Libuv is the base for Node.js, and then how this libuv actually achieved the uh, event loop and then also the reactor pattern in general. So let's suppose you have some clients, and then there is an event queue which will collect all those requests and then try to push it to the event loop. So this is an event loop which is single threaded, and in case if it's a blocking IO task, it will try to create some thread pool and it will assign those tasks. And then once the response is done, they will call back the response, and then it will be intimating the client as a response back. So it will try to this kind of complete infrastructure is being provided by libuv in general. So I'm quite curious how actually is this working and all. So what I did is I developed a a TCP/IP application out of it, where it can at least design at least workload around. I tested with our workload around 100 clients at a time, and then from there I got this kind of insight how actually this libuv is actually working in general. So mainly the key components are the event loop and the event queue and the execution handler in general. So let's see. Let's assume some problem here. So yeah, the problem here is I want to quit the event loop, but without any race condition and no memory errors. So this is my problem goal. And libuv as a case study, we are going to see how this can be achieved in general. So yeah, so this is the most interesting part of the talk actually. So what I'll try to do here is I'll try to use first thing is I have three things here. One way is to use semaphore to get out of the loop, and then another way is use to promise functionality, future and promise functionality, and then the third way is actually how the libuv does it. So yeah, so let's see this example. So here I made an assumption. Here these code, I mean this code is, you can assume it as a client. It has its own thread running actually. And then what I did here is I created a semaphore, and then I created the loop for the UV, and then I have an event loop actually. So which is having it has to run in the same loop. So what does the UV loop does is when it's triggered, it will trigger the run function and then try to start running the loop actually, and then it is waiting for the events. So then what I did is I started the close thread, and then I killed some time, like 2 seconds, and then I called the close function. If you see the close function here, it's quite simple. I'm just posting it so that I want to gracefully shut down the event loop. So how this is gonna be, of course, the waiting part is here, and then once the sempost is done, then we'll try to set the flag, and then it tries to quit the loop in this UV run. So and then close the loop, and then of course join them, and then close the loop and the sem destroy. So let's see how this is gonna be working with libuv under the hood. Okay, so the first thing is let's see how it will behave without the Valgrind. So we created some event loop, and we created a close thread, and then we created the of course it's left for 2 seconds the close thread, and then we are closing, and then event loop closing, and then the event loop closed. Seems like everything is fine. So let's quickly check how we can qualify, how it is qualified with Valgrind. What is Valgrind actually saying about this? It will take little time to run Valgrind. Yeah. Oh, 1 second. Maybe I didn't give the correct one. Okay. Yeah. So it's all done. So you don't have any errors. I think you are okay with the mem at least. Mem checker is okay. But let's try to see how it's gonna behave with Helgren. Okay. So you see the errors, and then we have a possible data race condition between, you can see, of course, the errors are repeated, no worries, but the main concern is with the UV loop close and then UV run. So it's not the right way how you will exactly shut down or come out of the event loop. So we need a different mechanism to, encounter this problem. So what I did is I did a little bit research again, coming back to C++ 17. I here try to do without a semaphore, but try to use a shutdown on the promise future from C++17 as an example. So how it will behave in case of this libuv. So that's the important part. So except the semaphore, I just use the shutdown promise example. There is nothing much change in this code. It's almost the same. So we can quickly see how it's going to behave. So the example here is ROM. All right, so we don't have any issue. It seems like the same results are repeating. We don't have any problem in general, but let's try to qualify this with the memory leak and the error detector. Yeah, so in general, there are no memory leaks. That's quite good. So let's try to see uh, how Helgren says about it. Yeah. So we have around 10 errors, and then again we'll try to see what is the race condition here. Again, it's the same. You have a U loop close and UV loop run. So then, okay, then this is definitely certain that it's not the right way how you quit a event loop or how you close an event loop. There should be something else in the application to exactly do this situation. So what I did is I digged up a little bit about libuv in general and try to understand how exactly we are going to do this, because it's quite important if you want to shut down your application gracefully, how you will achieve it. So okay, in general, everything is same, but the only thing is we have an event loop here, of course, but we have an asynchronous thread. Okay, so they have an asynchronous function, which is an handler. So we have to init that actually. And then this is a callback in general. So this will this will be done. This will be called only when you send a signal to quit. So let's suppose, yeah. So this is the simple thing. What I did here is I created an event loop. I created an async loop and gave the async thread, of course, and gave the loop. And then I started it. I ran it. So then it's running. Then what I did is I created the async thread again, and then I try to kill some time again as I did before. And then now suddenly I send a signal uh, to 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 quit. So to init the shutdown mechanism. So then once I set that, so then it will try to come here and then UV walk all the loop handles and all the handles, and then try to gracefully shut down the application. So it will try to collect all the handles and then try to gracefully shut down it. So okay, so the point here is we have to see how this is gonna from the technicalities, but from the writing perspective, I think it's quite okay. But let's also qualify with the compiler. So in general, what it does is it will try to create an event loop and an async thread, and then wait for 2 seconds, and then init the shutdown, and then you have UV waking all the handles, and then UV async CB callback and closed all callbacks, and then you see the after event loop message. So the event loop got exited properly, and then you got the message. So then it's quite good. We made a progress, I think. So let's see how this is going to be qualified with the mem check. Yeah. So seems all okay. It's all Valgrind is fully satisfied with this output. Let's see the critical part, how this is going to behave with the Halgrind. Okay, all cool. So we don't have any errors. You don't have any race conditions in general. So this code seems like working mostly in terms of race conditions. You don't have any kind of deadlocks thing. So it's all good. So this is it for the examples. And then let's quickly run through the final thoughts. Okay, so what exactly are the learnings from these kind of techniques or these kind of modeling? So first thing is you have to understand your model. What exactly you're trying to model, that is much more important than the requirement you set. So you have to minimize your shared state, mutable state. Of course, the critical section code should be carefully handled. And then also you should also design your model for a failure situation. You should know when it's going to failure, when it's going to fail, and then how to trim it and how to mitigate that problem. And then you should always test with a realistic workload. You should always give some stress test, example 100 clients on this, or if that is sufficient, you have to test with it definitely, and you have to qualify with both. With I also suggest GDB in this, but GDB cannot find all of it. Valgrind is really cool, but how we can do that in real time? How have we achieved is we try to simulate most of our code, and then the critical code which is there, which is like untouched, we try to make a Google test and we mocked it up actually. So that's how we made in the production we achieved the results with a workload, and then that's quite critical actually. And then identifying the critical section itself, it's quite important. So what are the techniques which we saw, and what are the other techniques which are available? So you can use futures and promises to a certain extent. Definitely you have to be careful in using it. And then reactive programming is a way to go, but the point is it's quite complex in general to code it for the first time. But once you set up the platform, I think it's quite easy to program it. Then you should also use non-blocking algorithms in general, and then you should use transactional memory wherever possible. This thing has to be tested. Transaction memory is always dealing about atomicity, so you should be able to really justify that whether this model is suiting the requirements and the processor, and it has to be tailor made actually. And then you should also use wherever possible immutable data structures. So these are some techniques. And then moving on to the performance considerations, this is quite really important because you cannot run the program anywhere. You can say like x86 is okay, then on the target it's not working. So then it's not the right model then. So you have to choose the right model for it. So then you should measure and profile. One such tool is Valgrind, of course, and then you have a couple of tools like Perf tool where you can measure the CPU efficiency and all, and then also see about load balancing and then work distribution in general, and then granularity of logs. There are two ways, like fine grain logs and the coarse grain logs. So fine grain log is actually locking a smaller section of code, but coarse grain is something like locking a larger part of the code with a mutex lock. So how this has to be justified, and between the interfaces, how do you lock it? So this is quite interesting thing to do, because you can have a lock inside lock, and then how do you synchronize between them, and then are there any deadlocks inside, so how do you detect them? So you should be carefully understand the lock mechanism, and then the concurrent data structure itself has to be trimmed and tailor made. Actually, it's not like it's not easy in my opinion. And then scaling on multi-core processors, so this is very crucial for parallel programming actually. So yeah, so this is it from my side. At times, the concurrency issues are hard to understand and debug, but solving them gives a big chance to step up the ladder in the software design. This is definitely a big thumbs up for whoever are dealing with concurrency. I would say they definitely have some learning in it, and then it will definitely step up them uh, to to really understand software design on how it's actually behaving both on the processor as well as the from an understanding perspective. So hope these are some of my references. These are really good references. You can try to go through them, and then hope you like my session. And thanks a lot once again for the CPP India for giving me an opportunity to interact with the Indian community, and then looking forward for the questions. Thanks a lot.
Okay, thank you, Ravikiran, for this wonderful talk, and you gave lots of refresher. And personally, I like that reactor pattern stuff a lot. Maybe I'll try that by my own.
Okay,
So before that, we have two questions. So I'll read it out for you. So
sure.
first question is, does the Valgrind need debug build or it works on release build as well?
Uh, it depends because I didn't optimize anything at the moment for the examples. It depends how you want to see it actually. If you want to optimize it out, but you will miss some things. So definitely, I would say it should be done with the debug build first. So try to understand the debug build first, and then in my opinion, release build, it's not Valgrind is actually it has a problem. It cannot work with a larger part of the code. So Valgrind has to be tailor made and stripped down to only certain part of the code where you think that is critical. You have to test it actually. So you can use other sanitizers in general for for bigger part of the code. But if you want to Valgrind to be used, you should be carefully trim them and use Google test or unit testing to make a executable out of it, and then you try to test the Valgrind so that you will get the quicker results as I did now. Because let's suppose you have a huge server client application. How do you test it with a Valgrind? It will take a lot of time to debug, and it will take a lot of time to create that image for Valgrind actually. So in my opinion, you have to cut short your thinking, and then you have to break down your logic, and then give simple inputs to Valgrind, and keep the critical code same. Other things you have to mock it up. So using a Google test as an example. So that I hope I cleared the question, and
Yeah.
then yeah.
Okay, so the next one is, does Valgrind have any good tool for shared atomic race condition across threads?
Valgrind, yes, that's a good question actually. Valgrind does not, in general, does not understand atomicity fully. So what you should do is you have to write your own atomic classes by yourself. So in general, what it does is if you give an atomicity, generally atomicity is what I assume is you have to lock that variable. So you have to make sure that you have to lock. So what we did here is we also had the same issue where we could not make a Valgrind understand atomic. So this is a quite critical thing. So what we did is we made a special arrangement so that whenever we try to run the Valgrind, it will try to override the atomic variable as a mutex lock and then lock the variable in general. So this is how we have to tailor made it. For normal without Valgrind, we tried using atomics. That's the simple way of going. But if you use atomics using Valgrind, you will get false positives. Definitely you'll get all false positives, and then you will not understand whether this is a race condition or you have to look for an answer or not. So better, my suggestion is do not use atomics for Valgrind. If you want to use it, you have to definitely change that atomics, or you have to find a way how you can change that atomic variable to have a lock, and then lock it and then run the Valgrind. So this is the way to go actually.
Okay, okay, that's good. Next one is, can we discuss some drawbacks of reactor pattern over the standard master slave thread pool?
Reactor pattern is definitely way to go. I would definitely encourage anyone to try for themselves, because you will learn a lot in it. Because synchronous way of programming is really not really up to the mark, in my opinion. It's always you'll find some of the other problems. So but the reactor pattern, what how it is making the difference is, as I explained you clearly, so it will not block any of your request. So it will try to create its own thread pool, and it try to give the task for the thread pool to, you know, go through the work, and then the event loop keeps running, and then once the tasks are done, it will respond back. So initially, reactor pattern is a tough thing to understand. I face a lot of problems understanding the reactor pattern, because it was quite astonishing for me. I could not understand the topic of libuv in general. So then I digged up a lot, and I played around it a lot with the libuv. I also went through their unit test examples, libuv. Then I understood, okay, this is how it behaves, and you have to really understand that initially writing the reactor pattern is quite complex in general, but the results is really great. Yeah.
Okay, okay, great. Okay, the next one is, can we use sanitizers like ASEN or TSEN instead of Valgrind? Any situation where one
Yes,
is
I
better?
already used it. I think I already showed you in the CMake list. I already used thread sanitizers, which are provided from GCC. They are okay till certain extent, but they will not fully give the race condition picture as well as your mem checks. Sometimes they are not working correctly. So definitely you should have two builds. One debug build, which is having this sanitizers, and another build which is having this exclusive Valgrind. And when it comes to concurrency, definitely go with Valgrind and GDB in general. So these two are the heads up tool actually.
Okay, okay. And the next one is, do you use standard vanilla locks in real-time code as well?
Can you define what is the vanilla locks here?
I believe vanilla locks is some, means I'm not sure, just giving a guess. It's some raw lock unlock thing. Mutex lock, mutex unlock something.
No, definitely it's, yeah. I definitely use it with a lock guard or a unique lock. That's for, and lock and unlock are not preferred. Definitely leave it to RAII. You can check the concept of RAII. So let the compiler do it actually for yourself. Unlocking, you should never take care of it. It's done. I think we are done with it. So yeah, I think you should use always a log guard, in my opinion, and then a unique lock in general, and then scoped lock actually. These are like a way to go.
Yeah. Means I think, if until it's not required, leave all these things for compiler to take care of all
Exactly.
this stuff.
Exactly.
Don't overmaster it, or
Yeah. Yeah.
overextend is not
Yeah.
good.
I think we have one more question. Yeah.
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 Isn't
Yeah.
using lock
Good.
strictly prohibited in real
In
time?
real time, yes. So it's a good question, actually. In my opinion, it's a very good question. Whoever asked it, I think it's a good question. So we are talking more about logs. What exactly are they required? Yes. So how do you scale it? So the thing is, you have to understand your model, and then you have to check your performance actually, performance on real time, and then you have to give real time loads in order to check the how the logs are actually behaving. And then let's suppose a good example is you have lock free data structures and locked data structures. So these two are quite different. And then lock free data structures uses mostly atomicity, and then they are pretty hard to design in general, but but the point is they are also pretty hard to design and also pretty hard to maintain. And the point is performance. How do they perform? That has to be really checked in taking the call if you don't want to use lock. So how they are actually performing, if you have a lot of race conditions, if you are not clear enough how the code actually behaves, then it's not up to you to use that lock free data structures. So the best thing what I would suggest for concurrency is try to understand your model, and then you should be able to predict the output actually. So you should be able to see all kind of scenarios when the lock will work, when the lock will not work, and then it should be more predictable. It should be more predictable code. Then you get the control over the concurrency in general. If not, it's gone. I mean, it can have any kind of scenario where you deadlock the situation, and then yeah,
Right.
it should be carefully tailor made. The
Yes.
concurrency is one such topic where you have to really put your heads down and then try to see what theory is saying, what compiler is saying, how it is performing, and then trying to find the match of it. So then you get the understanding how concurrency is actually. So till that time, you have to keep learning.